Okay, so in the previous video, we get this new updated system. Okay, in some sense, this is still the same system. What's different is that now we keep our basic columns satisfying our requirements. Okay, why do we want to do that will be clear here. The key is that we want to know how to do the next iteration. First, I want to know for x2 and x4 which one should enter, okay, because they are currently non-basic. For x2 and x4, I want to know who should enter. For x2, things will be good because when x2 enters, okay, when x2 becomes larger, z should also become z should become smaller, and I want to minimize z. That's good. But for x4, if x4 enters, becomes larger, z will also becomes larger, and that's bad. Why can I be sure about this? It's because there is nothing related to the basic variables. Okay. Remind yourself that when you change the value of the non-basic variables, typically, when you change non-basic variables, you need to also change basic variables, right? To satisfy these equality constraints. But because the coefficients for basic variables in the objective value have been updated to 0, you don't need to worry about how those basic variables will affect your z value. That's not going to happen. All you need to do is to worry about what's going to happen at the non-basic variable that you enter. Okay? So that's why you can make this concrete, precise conclusion. So now we know the only thing we may enter is x2. And now for row 1, there is only x3 as a basic variable. x4 must be 0 forever, in this iteration, and x1 does not appear. So you know when x2 goes up, x3 will go down to maintain this equality constraint, and the amount of x2 we may increase will be 4/3 as the ratio of 2 to 3/2. And for the second constraint is almost identical. We may increase x2 up to 8 because we may adjust x1 accordingly. And x1 is currently 4, and x1 can be decreased to 0, and x2 can be at most 8. So we know for x3 and x1, x3 will become 0 before x1. So x3 will leave the basis. Okay? So x3 leave, x2 enter. The basic variables should become x1 and x2. And given this information, okay, we know, x1 is basic, x2 should become basic. So we should give an identity matrix here and make this number 0. Okay, this number should become 1 and this number should become 0 for we to get an identity. So now it's time to do another row operations. So constraint 1 should be multiplied by 3/2 so that we can make this number 1. Okay, and then I should multiply the updated constraint 1 by -1/2 so that we can eliminate this thing, get it into 0. And then I should multiply the updated constraint 1 by -2 and add it to, okay, this should be constraint 0. Okay, so that I can eliminate the objective part into 0. Okay, exactly what we did for the first iteration. And by doing that, okay, now this part is clear, and that's what we need. We get this updated system. This system is telling us a very important thing. Okay, so first, x1 and x2, they are basic variables, and x3 and x4, they are 0. So x1 is currently 10/3, x2 is currently 4/3. And also, these guys are 0, so the z value is currently like this. okay, a better solution than the previous parts. And also, it's clear that now there is no more improvement needed, because when we increase x3, things will become worse. And if we enter x4, things will also become worse. Okay, these things are negative. If we increase x3, for example, then z must also be increased so that we may maintain this objective row. Okay, and we want to minimize z. That's not a good idea. So when we see all these numbers being negative, okay, all the coefficients in the zeros row being negative, then we know that this is an optimal solution. We are done. Okay, or make it more precisely. Make it more precise. When all the coefficients in the zeros row are non-positive, okay, 0 or negative, then we're done because we have no way to improve our objective value. So let's try to visualize this example. The initial basic feasible solution for the two variables x1 and x2, they are 0, 0. So originally we are here. In one iteration, we move to 4, 0. In the next iteration, we move to the optimal solution 10 over 3 and 4 over 3. Okay, you may see that indeed we are moving along edges until we get to the optimal solution. Okay, so as a brief summary, when we run the simplex method, first we need to find an initial basic feasible solution with the associated basis. In general, okay, we may be not so lucky as we did in the first example we solved. But you may want to think about, what if you do not have that initial identity matrix? Okay, there may be something you need to do. We're going to discuss that in the next lecture. And then, among those non-negative variables with positive coefficients in the zeros row, we want to choose one to enter. Okay, here, I am actually saying this should be non-basic variables. Okay, among those non-basic variables, I need to choose one to enter, and that one must have positive coefficients in the objective row. If there is no one, then I can terminate the process and say that the current basic feasible solution is optimal, because I cannot improve further. And then I need to do several ratios from the basic column and the right-hand side column to determine which basic variable should leave. One problem you may want to consider is that, what if there is a tie, okay? Multiple rows all have the minimum ratio. Or what if the denominator is 0 or negative? Well, we didn't touch that in the first example, but probably you want to think about it now. Anyway, suppose we find one thing that has the minimum ratio. Then we know that's the first, that gives us the first basic variable that is going to become 0. And we know that variable will leave the basis. So now we have entering variable, leaving variable, we have a new basis, and then we need to update the system to fit the requirements for the basic columns. We need to create an identity matrix in the constraints, and we need to get zeros in the objective function for the basic columns. Once we have that, it will be very easy to repeat here to do those entering and leaving variables. Okay, so we need to do the calculations, and there's one thing we may do to make the calculations easier. Okay, it's just like when you do for Gaussian eliminations. We don't really need to write down all those x1, x2, x3, whatever, right? We only need to use a tableau to record those information we need. Okay, so for this initial system, we actually do not need this column, right? Because this column will never change, so let's remove it. And also for these coefficients, we also do not need them. So this system can be expressed conveniently in this way. Everything are copied from the system, but we only copy numbers. For the last part, okay, here, if you want, you may indicate to remind yourself that these are the values of the basic variables, okay, so that when you see this, you immediately know the current basic feasible solution is 0, 0, 6, and 8. The basic columns here, okay, the second and the third and the fourth have zeros in the zeros row and identity matrix in the other rows. The identity matrix tells us which row is associated with x3 and which row is associated with x4. Okay? Because in this row, the identity matrix has 1 here, so that means this number corresponds to the value for x3. For this row, because it's in the last column that having 1, so this corresponds to the value for x4. And finally, if we have a positive number in the zeros row of a non-basic column, then that variable can enter, because that's how the objective value z can be improved. So calculations may be carried over with tableaus exactly. Here we know x1 should enter. And why do we know the x4 should be leave? Because we know when we are looking at the first column, we do a ratio test. Okay? 6 divided by 1, 8 divided by 2. This ratio is just 4. Okay? 4 is smaller than 6. So we know we need to make this number 1 and the other numbers 0. And we do that exactly by doing some row operations. And then we do it again. This number is positive, so we enter this second row, or x2. And then ratio test again. 2 divided by 3 over 2. 4 divided by 1 over 2. This part, this number, this row has the smaller ratio. So x3 should leave the basis. We do a second updating to get this identity matrix, zeros here, all the numbers here are negative, and we're done. So to enhance your understanding, let's consider another example very quickly. Now we have 3 constraints with again 2 variables, but now we have 3 slack variables to make the standard form. Our initial tableau is here. Okay, we still have 2 non-basic variables and 3 basic variables. Here, this number is -1. Again, that comes from the objective function. Here we are maximizing x1, and anytime when you prepare the initial tableau, those numbers are negations of the original objective coefficients. Okay, because you are using an equation with z to get this, and that's why this number is -1 instead of 1. Now, because we are solving maximization problems, we look for negative numbers in the zeros row. Why? Here, this negative number means the zeros row is z minus x1 equals 0. If we want x1 to become larger, then the z value will also become larger, right? And that's going to make z value larger. For the maximization problem is a good thing. Starting from now, we will call these coefficients a special name, reduced cost. Okay? Reduced cost measures what will happen to the objective value when you increase those non-basic variables. Okay? And for maximization problems, we look for negative reduced costs. Once we decide this column should enter, we will do a comparison for these ratios. Okay? For the entering column and the right hand side column, for each row, we will do a ratio. For the first row, here we get 2. For the second row, we get 4. What's happening in the last row? Okay, here the issue is that these ratios are measuring how large the non-basic variable may be according to that constraint. So for the first constraint, when you increase x1, x1 can be at most 2. Because when x1 goes up, x3 will go down, and at last, eventually, your x1 can be at most 2. For the second row, your x4 will go down, and eventually you will get x1 to be at most 4. How about the last constraint? The last constraint is actually x2 plus x5 equals 3, right? When you increase x1, it has nothing to do with x5, and that's why you have this number 0. Okay? That means when you increase x1, x5 will not change, and that means you have nothing to worry about for the last constraint. So, here, we do not need to worry about this one. Among the first two ratios, we pick the smaller one. So we know x3 will be the leaving variable. So now x1 enter, x3 leaves. We focus on this number. We're going to call this number the pivot. Okay, and we say we pivoting at this number, we pivoting at 2, so that we make the pivot 1, and all other numbers in the same column 0. We do that with the elementary row operations, and if you carry out the calculation, you will get this. And you can see that this number 2 is now the value of x1 instead of x3. The basic feasible solution here is 20043. Here, how may we continue? Again, we look for negative reduced costs, and now x2 has that. So x2 should enter. Once we know that, we again do a ratio test by comparing all these ratios. For the second and the third one, they are simple. The ratio is 2, the ratio is 3. How about this? This negative denominator tells us that the first row do not need to enter the ratio test. Why? x1 minus 1/2 x2 plus 1/2 x3 equals 2. This is what's happening in the first row. When x2 goes up, x1 will actually goes up, right? So x1 does not become smaller. x1 will never become 0. So you don't need to worry about the first constraint. The first constraint does not limit the increase of x2. Only the other two constraints do. So this negative number tells you that you don't need to worry about that. For rows 2 and 3, row 2 wins with the smaller ratio. So x4 will leave the basis. Now x2 will enter, x4 will leave, we pivot at 2. The second iteration, blah 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 blah. Okay, you calculate all the numbers, you get this. You get to the third basic feasible solution, which is x1 is 3, x2 is 2, 0, 0, 1. Okay, and then the new objective value is always in the corner, is 3. Is this guy optimal? It is, because all the numbers here are non-negative. Okay, we look for negative numbers, negative reduced costs, but now all the reduced costs are non-negative, so we're done. Okay, and as a convention, we would like to write the optimal solution as x star and the optimal objective value as z star. Whew. So finally, the three basic feasible solutions we have passed is the first one, goes to the second one, and then stop at the last one. Again, we work with edges. We move along edges until we reach the optimal solution. Okay, so that fits our intuition. So, as a very brief summary, in this lecture we talk about the simplex method. We start from standard form problems to basic solutions, basic feasible solutions. We know that we search among basic feasible solutions by moving along edges. And the algebra contains several iterations. In each iteration, we first look for basic entering variables and then leaving variables. And after that, we do a pivoting to update the system to maintain something we need so that we may keep doing this iteration until we find the optimal solution. Okay, so that's the end of the introduction of the simplex method. Thank you.